Welcome back. Today we're exploring knowledge distillation, the process of compressing a large, powerful model into a smaller, more efficient one.
Distillation is crucial for deployment because large models, while capable, are often too expensive and slow for real world applications.
Let's start with the core concept. What is knowledge distillation?
Knowledge distillation trains a smaller student model to mimic the behavior of a larger teacher model.
The student learns not just from the labeled data, but from the teacher's predictions, which contain richer information.
Instead of just learning this example is class A, the student learns the teacher's confidence distribution across all classes.
This softer information helps the student learn faster and generalize better.
The technique was popularized by Geoffrey Hinton and colleagues, though the core idea has earlier roots.
Let's talk about how distillation actually works.
You start with a trained teacher model, typically large and high performing, and a smaller student model with fewer parameters.
During training, you feed the same input to both models.
The teacher produces a probability distribution over outputs. These are called soft targets or soft labels.
The student is trained to match both the hard labels, the actual correct answers, and the teacher's soft targets.
The loss combines these two objectives. You might use cross entropy against hard labels plus KL divergence against the teacher's distribution.
KL divergence measures how different two probability distributions are. Minimizing it makes the student's predictions similar to the teacher's.
You typically use a temperature parameter to smooth the teacher's distributions.
Temperature divides the logits before applying softmax. Higher temperature makes the distribution more uniform, exposing more information about relative confidences.
For example, with temperature 1, the teacher might output probabilities zero point 0.9 mile, 0.05, 0.05. With temperature 5, it might be more like 0.5, 0.25, 0.5.
The software distribution shows that the teacher considers some wrong answers more plausible than others.
This information about the similarity structure of outputs is valuable for the student.
After training, you use temperature 1 for the student. During inference, you only use high temperature during distillation.
Now, how much can you compress? What's the trade off between student size and performance?
It depends on the task and data, but you can often compress by 5x to 20x with modest performance degradation.
For example, Distilbert is about 40% smaller than BERT, but retains 97% of its performance on glue benchmarks.
TinyBirt and MobileBirt push compression further with specialized distillation techniques.
But there are limits. If the student is too small, it simply can't capture what the teacher knows.
Let's discuss different types of distillation for LLMs.
Response distillation trains the student to match the teacher's output distributions, as we just described.
Feature distillation also matches intermediate layer representations between teacher and student.
You add losses that encourage the student's hidden states to be similar to the teacher's.
This provides supervision not just on outputs but on the internal representations.
Attention distillation specifically matches attention patterns between teacher and student.
The idea is that attention heads learn meaningful patterns, and transferring these patterns helps the student.
You can combine multiple types of distillation for better results.
Another variant is progressive distillation, where you distill in stages.
You might first distill to a medium sized model, then distill that to an even smaller model.
This can sometimes work better than directly distilling to a very small student.
Let's talk about data for distillation.
You can use the original training data if available. The student learns from both the original labels and the teacher's predictions.
But you can also distill using unlabeled data or even synthetic data.
The teacher generates predictions on unlabeled examples, and the student learns from these.
This is powerful because you're not limited by labeled data availability.
You can even have the teacher generate synthetic training examples and pseudo labels for the student.
This is especially useful when the original training data is proprietary or unavailable.
Now, what about distilling for specific tasks versus general capabilities?
Task specific distillation optimizes the student for a particular task.
The student might be much smaller but perform well on that specific task.
General distillation tries to preserve broad capabilities. You distill on diverse data covering many tasks and domains, creating a smaller general purpose model. Models like Distill GPT-2 or smaller instruction tuned models are examples of general distillation.
Let's discuss architectural differences between teacher and student.
The student usually has the same architecture as the teacher, but fewer layers or smaller dimensions.
For example, a 12-layer model distilled to 6 layers.
But you can also distill across architectures from a transformer to a more efficient architecture.
This requires careful alignment of representations since the architectures differ.
One challenge is deciding which teacher layers correspond to which student layers for feature distillation.
Common approaches include uniform spacing or learned alignment.
Let's talk about distillation for deployment scenarios.
You might distill for specific hardware, creating a student optimized for mobile devices or edge deployment.
This might involve not just fewer parameters, but also constraints on operations to match hardware capabilities.
Distillation can be combined with quantization, reducing parameter precision to 8-bit or 4-bit.
You might distill a large FP32 model to a smaller model, then quantize that to ENT8.
Or even distill with quantization aware training, where the student is quantized during distillation.
This ensures the student learns to be accurate even with reduced precision.
Another deployment consideration is latency.
Smaller students are faster at inference. A 6-layer model might run 2x faster than a 12-layer model.
For applications with strict latency requirements, this speedup is crucial.
You can distill specifically for latency targets, train students of different sizes, and pick the smallest that meets your latency needs.
Let's discuss self distillation, an interesting variant.
In self distillation, a model acts as its own teacher.
You might train a model, then use its predictions to retrain itself.
Surprisingly, this can sometimes improve performance, acting as a form of regularization.
Or you might use different augmentations of the same data for teacher and student in self distillation.
Another form is ensemble distillation, where multiple models act as teachers.
You average predictions from several teachers and distill that knowledge into a single student.
This transfers the ensemble's collective knowledge into one efficient model.
Now, what are the limitations of distillation?
First, you need a good teacher. Distillation can't create knowledge that isn't in the teacher.
Second, very aggressive compression leads to performance degradation. There's a limit to how small you can go.
Third, distillation requires careful hyperparameter tuning, temperature, loss weighting, learning rates.
Fourth, the student might inherit the teacher's biases and errors.
And fifth, distillation still requires training time and compute, though less than training the large model from scratch.
Let's talk about evaluation of distilled models.
You should evaluate on the same benchmarks as the teacher to measure retained performance.
But also measure efficiency, inference speed, memory usage, energy consumption.
The goal is to find the best performance efficiency trade off for your application.
You should also check for failure modes the teacher didn't have.
Sometimes students develop brittle behavior or lose capabilities in edge cases.
Finally, let's discuss the future of distillation for LLMs.
There's ongoing research into better distillation objectives that transfer more knowledge.
Work on distillation aware architecture search, finding student architectures optimal for distillation.
Exploration of distilling multimodal capabilities or specialized reasoning abilities.
And interest in continuous distillation, distilling from continuously improving teacher models to keep students up to date.
So, to recap, knowledge distillation trains smaller student models to mimic larger teachers. It uses soft targets and intermediate representations for richer supervision. It enables significant compression with modest performance loss. It can use unlabeled or synthetic data, and it's crucial for deploying LLMs efficiently in resource constrained settings.
Next episode, we're exploring retrieval augmented generation, combining LLMs with knowledge bases for grounded, up to date responses.
Thanks for listening.
Until next time, keep learning and stay curious about AI.